Good day, I'm Norman Wildberger. In today's video, we are going to sort of reach a culmination of this course on Boole's logic, where I show you a systematic way of solving essentially the holy grail of propositional logic going back essentially thousands of years, but at least to Leibniz, which is to find a mechanical or arithmetical or mathematical way of systematizing reasoning. And I'm going to talk about the algebra of Boole procedure, which you already have some exposure to now, so this will be a kind of a recap, but I'm going to show you that the technology works in a rather more general situation. So we're going to be looking at situations where the premises of our argument are not quite so simple. They can be rather more complicated statements involving some variables A, B, and C, which correspond to atomic propositions about which we know more or less nothing. So there are these premises, in this case 3 of them, and they're each rather complicated, and then there's a conclusion. And the idea is to try to establish this conclusion on the basis of these premises. So let's have a look at the premises. First one here is A or B implies C is equivalent to A. Okay, that's a legitimate logical operator, equivalence. Here's another one, involves A equivalent to B, implies this combination, not A or B and C. And the third premise, A and B or not C, all of that, and B implies C. Okay, so those are the 3 premises, and if we assume each one of these is true, then we're trying to conclude that C implies B is also true. All right, so in this kind of situation, or more complicated ones where perhaps we have a lot more premises and they are not generally very simple, it's a major challenge to try to suss out which way to go using inference rules or clever choices of identities. What I'm going to show you is that the algebra of Boole provides us with a systematic approach of basically reducing this kind of problem to a purely mechanical, mathematical simplification, okay, which is really a kind of a pinnacle, really, of a propositional logic, I think. Now, there's really 2 steps to this procedure. The first step is to convert all the statements into Boole polynumbers. So, for example, let's say the first premise, let's call it X. A or B implies C is equivalent to A. That statement, when we replace the logical connectives with their corresponding arithmetizations in the algebra of Boole, ends up yielding the following Boole polynumber: 1 plus A plus AC plus BC plus ABC. The second premise, which we might call Y, turns out to reduce to A plus B plus C plus AC plus BC. And the third one, which we might call Z, turns out to be 1 plus B plus C plus BC plus ABC. And I remind you that with the algebra of Boole, very happily, these are canonical objects. Anybody doing this, if they do it correctly, will arrive at exactly the same answers. So we do not have the ambiguity that we have in the Boolean algebra point of view, which currently is the framework both for electrical engineering and for classical propositional logic courses. Okay, so this is a new framework that allows us this crucial property that the results of simplification are canonical, so we can check and everybody has the same answer. And the conclusion, of course, we also have to convert that. C implies B is, of course, 1 plus C plus BC. Now, I'm going to check X, and I'll explain how this is derived, and I'm going to leave Y and Z for you as exercises. See if you actually agree that I've done it correctly. Okay, so the idea is to take this thing and simplify it to get this, and also to take this thing and simplify it to get this. We are now going to have a look at the first one. Okay, so X was A or B implies C is equivalent to A. So we want to replace all these connectives with their algebra of Boole equivalence. All right, so A or B. We all know, I hope, that that's the same as A plus B plus AB. And what about C is equivalent to A? that's a connective that we haven't seen that much before, but I remind you that in the algebra of Boole, it's expressed as 1 plus c plus a. Let me just remind you about that. So when a and c are the same, in other words, both 0 or both 1, then their sum is always 0, and this total is always 1. Okay, so if they're the same, we always get 1. On the other hand, if they are different, one of them is 0 and the other one's 1, then this sum is 1 and the total here is 0. Right? So this is indeed an arithmetization of this logical connective. Okay, and we still maintain the implies there momentarily, and now we're going to replace that. Okay, so this implies this. We write that as 1 plus the first term, a plus b plus ab, plus the product, a plus b plus ab times 1 plus c plus a. And now we have to expand and simplify using Boole reduction. Okay, so what do we get? Okay, this will be a 1. Now this a plus b plus ab happily cancels with the a plus b plus ab that we get by multiplying this by 1. Okay, that just dies. And so we just have a plus b plus ab times c plus a. So we multiply by c, we get ac plus bc plus abc. And now we multiply by a. So a times a is a, ab, and a times this thing is another ab. Okay, what are we getting here? So there's some cancellation. What cancels? These two ab's will cancel. And I guess nothing else, so we'll have 1 plus a plus ac plus bc plus abc. And that is, looking over here, that is the same thing as I claimed earlier. Okay, so we've reduced x or simplified it or expressed it purely in terms of the algebra of Boole, and this is a Boole polynumber. It's in canonical form because all the coefficients are either 0 or 1, and there's no powers bigger than 1. Great, so we do that for all the ingredients, all the premises, and all the conclusions. And then we proceed to step 2 of the procedure, which is the following. We verify that this composite expression, premise 1 times premise 2 times premise 3, if there are 3 premises, as there are here, implies the conclusion. Okay, so we multiply the premises. That's the mathematical equivalent of taking the ands of those. We're taking the first premise and the second premise and the third premise and so on. And we're trying to show that together that implies the conclusion. And the way we're doing that is we're taking this entire expression and we're evaluating it. Okay, so this is just another expression in the algebra of Boole world, and it reduces to a Boole polynumber, and we want to prove that that Boole polynumber that it reduces to is exactly 1. It doesn't have any of these a's, b's, ab's, abc's, etc. Just 1. That means it's always equal to 1. That means this is a tautology. That is then the end of our derivation. We have, if we are able to do this, we have shown that the premises really do imply the conclusion. And that's the outline. It's very conceptually simple. But in practice, maybe not so simple to actually do because there might be a fair amount of work involved. Let's have a look at how our example runs out. Okay, so suppose that we've managed to simplify all of our premises and our conclusion. So there's premise x, there's premise y, there's premise z, now all expressed in the algebra of Boole as a Boole polynumber. And here is our desired conclusion, which we're calling w. And now what we want to do then, according to this second step, is to prove that the composite of x times y times z actually implies w. What does that mean? It means that we have to take these expressions. There's x, there's y, we have to multiply them. We also have to multiply by z. Then we have to form an implication, and the w's right here. So this entire thing here, we have to evaluate it. And hopefully, we'll get 1. Hopefully. So what we want to do generally in this kind of situation is we want to simplify ingredients in a bigger expression. So for example, if we take the left-hand side, the product of x y, and z. We want to simplify that first. So we could do that by multiplying the x times the y. Now, at first glance, that's a fair amount of work because this thing has 5 terms and this thing has 5 terms. So altogether, there's actually 5 times 5, 25 different multiplications that we have to do. That's true. But of course, with the Boole reductions, a lot of those things are going to end up canceling with other ones. And whenever we get powers, we rub them off, and that will help with the cancellation. But nevertheless, there is some work to be done there. And when you do that, you can check that what you get is b plus c plus ab. So all the other things have canceled. So this is the advantage in doing the reduction sort of whenever we can. Whenever we can, we have some expression, we will reduce it to simplify it. So now the whole thing becomes this thing here, which is the new product of x times y, times this z term. Okay, so then leave it to you. Same kind of thing. We expand it out, collect terms, cancel, rub off powers, etc. And it turns out that it all reduces to ABC. So that the crucial expression that we want to simplify is ABC implies 1 plus C plus BC. Okay, now that's very manageable because we know how to do that. That's an implication. So it's 1 plus the first term, ABC, plus the product, ABC times 1 plus C plus BC. And what do we get? Well, the ABC here cancels with the ABC here. The ABC times C is ABC, but so is ABC times BC. That's also ABC, so those two cancel. And all that we're left with is the 1 at the beginning. That's what we want. That proves that the argument is legit. This verifies that, yes, indeed, the product of the 3 premises, x, y, and z, does imply W. And we've done it by doing a reduction, basically an arithmetical process involving grade 9 simplified polynomial algebra. Although admittedly, possibly in a rather extensive format. So our grade 9 student is getting lots of good practice at their polynomial arithmetic by doing this kind of thing. By the way, this is actually quite a good thing for high school students to do, to learn this. This is a great application of polynomial algebra in their lives. Something for educators to think about. So if you've appreciated what I've just done, you will, I hope, realize that this is a real watershed moment in the story of propositional logic. Because what we're doing is we're sort of completing this long-standing ambition that really goes back to Aristotle and the Stoics. This idea of trying to make mechanical the process of reasoning in a logical kind of way. And that was actually first pretty clearly enunciated by Leibniz. So Leibniz dreamt about having this kind of mechanical or mathematical way of resolving arguments. And of course, what we're doing is we're using the algebra Boole. We're taking the orientation that George Boole laid out for us in really his first paper on the subject. Okay, he said, this is the way that we move forward in the direction of Leibniz's dream, of providing a mathematical framework for modeling philosophical logic problems and then being able to solve them in this purely mathematical context. Of course, what I've done is I've taken George Boole's paper and looked at it and sort of extracted what I think are the essences of it from a modern point of view, okay? But basically we're really taking Boole's row that he's set out for us. So to try to find a purely mathematical method for verifying reasoning. That's what really we've been able to do. So in a nutshell, what does it amount to? It amounts to this. We take the various premises, say P1, P2, maybe there's n of them. We convert all of them into the algebra of Boole. So replace all the arrows, replace the ors, the ands, and so on, with just additions and multiplications. We replace the conclusion also with a Boole polynumber. We create this composite expression which captures the idea that the product of the premises implies the conclusion. And then we systematically reduce this thing, just using the Boole reduction formulas, and hopefully we get 1. And if we do, then we have succeeded in our task. And it's a purely algebraic reduction, which requires no memorization of prior clever identities or rules, which is completely straightforward and which everybody can agree to. The end result is canonical. So whether it's 1 or not is not debatable. If you get a Boole-Pauli number, either it's going to be 1 or it's not, and that's the end of the story. Now, this algebra of Boole procedure for mechanizing logical reasoning is especially suitable for computers. So computers, computer algebra systems, are super good and efficient at working with polynomial arithmetic. It's one of the actually great achievements of sort of the computer science community in the last few decades is to develop all these tools to allow our computers to do this fundamental algebra very quickly. It's really great. And if we could augment that great achievement by a few more additional things involving Boole reduction algorithms, which I've mentioned to you before, then we have a system which is just perfectly designed to very, very quickly deal with even very big problems here. You know, millions of terms, a computer can deal with that. You have enough RAM and a good processor, it can do it. Especially when you combine it with the algebra of Boole reductions that you want to be incorporating into the procedures. Okay, so it's very powerful. But we have to admit that by hand, this can be onerous. This procedure that I've laid out for you involves multiplication of all these premises. Okay, so if each of the premises is a rather long thing, especially if you have lots of variables, you're multiplying this 10 variable thing by that 10 variable thing by that 10 variable thing by that 10 variable thing or whatever. So that can be a lot of terms, even if you have Boole reduction at your disposal. So fortunately, there is actually a second method which I'm going to show you. Okay, a second method for solving this fundamental problem. So I've already laid out the primary method now, okay, but I'm going to show you now a second method, which is a little bit clever. That's not so easy to find if you're just doing propositional logic. So what we're going to do is we're going to go back to our earlier discussion of the logic gate story, the electrical engineering part, and go back to what we're actually doing there. And particularly, we're going to be drawing upon the Boole-Mobius transform, which was this really key kind of cute transformation between Boolean functions and Boole-Pauli numbers. So it turns out that by exploiting that thing and understanding that Boole-Mobius transform computationally a little bit better, we're going to have a viable second alternative to solving this fundamental logical procedure for verifying reasoning. So we're going to talk about that in our next video. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.